So we know trigonometric functions, sine, cosine, tangent, secant, cosecant, keeps on going. We did the introduction to trigonometric functions in Appendix D, Unit 1. Hopefully you still remember. If not, go back, watch the video, review, and then come back when you do the homework assignment. So I'm going to start with the derivative of sine x, and that would equal to cosine x. Really? Lovely. The derivative of cosine x would equal to negative sine x. Good. If you open the textbook and if you look at the very front, you would see table of integrals and table of derivatives. You can see that with the ebook as a table where you can click and get the formula sheet. My principle, anyone can come up with the formula. The reason is why. So I'll explain for this and we can extend it to cosine also. But for me to do that, I need two important limits. Let's see if you remember this. Either we did it in class, or there's a problem definitely on the homework, or both. We did it when we did limits, and we used a calculator to find that limit. Yes. Do you want to try and calculate it again? Go ahead, graph sine x over x and tell me what happens as you get closer to 0. This I don't believe we did it. Might be in the homework. So the limit for that is simply 0. I need these two to come up with the derivative of sine x and cosine x. Again, anyone can come up with the formula, but you need to know why. My poor artistic abilities aside, we may agree that this is somewhat of a sine wave. Yep. Okay. There's a reason why I'm from this. What would a cosine look like?
It would look like a phase shift like over there.
It'll be what?
It's like basically if you take a phase shift and you went the other way.
Do change, I labeled it incorrectly. Pi over 2, pi, 3 pi over 2, 2 pi. So there will be a phase shift of 90 degrees. So let's see if we can do this. And what happens exactly at pi for cosine? Right.
Oh, the
Cosine pi.
-1.
-1. Okay, let's do this right. Okay. cosine 2 pi, positive 1. Good. It's going to keep on going. So you look at the sine function between 0 and pi over 2. What is happening to the function, the sine curve? Is it increasing, decreasing? Increasing, right? It's going up from here to there. I did the derivative, or I wrote the formula for the derivative, and I told you the derivative of sine x is cosine x. Yes? Come on. It's decreasing. How could it be right? Do you follow my question? So from 0 to pi over 2, sine function is increasing. I took the derivative of sine, and I said it is going to be cosine. So cosine is going to describe the behavior of sine. And you look at it, and it's decreasing. How could it be right? Go ahead, Shia.
I'm just taking a guess, so like, you take the derivative, it's an instant rate of change, right? But at a certain point, so probably at a certain point, it's still going up.
How? How do you know it's still going up? This is decreasing.
Because you're looking at the graph in total, right? But you have to look at it like 1 point. I don't know.
So this is increasing, the cosine is decreasing.
They're still approaching the same point though, aren't they?
Come again?
They're still approaching the same point though, aren't they? Even though.
Well, yes, they are periodic. I guess you're not following my question. So we agree that sine is increasing between 0 and pi over 2. Yes. The derivative of the function is going to tell us what the function is doing at each and every point. Yes, it's going to tell us either if it's going to go up, go down, it stays 0, because it is the instantaneous rate of change. So this should explain the behavior of that function, correct? In terms of increasing and decreasing. So sine is increasing between 0 and pi over 2, and cosine is the one that is describing the behavior of sine, but it is decreasing. Is it making sense? No. Why? What? He regrets shaking.
Yeah, no.
Like,
I feel like I remember I don't remember the reasoning behind it, but I know that there's a relationship between that behavior as to why it does that.
so does decreasing mean negative? No. Lewis, what?
Because even though, although it's going down, doesn't mean it's negative.
It's on to the negative numbers.
Just, what did you say?
Sorry.
No, I just gave.
Just because it's decreasing doesn't mean it's going to the negative numbers. You could have 100 going to 99, but it still would be positive.
I was just gonna say because of what you said with the describing how sine behaves in that quadrant. So since you're describing a positive behavior,
Okay, so if you look at this curve, every single value of cosine is positive. Do you agree? So positive, 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 and they are decreasing. So the magnitude of that curve starts at 0 and it's approaching 0. Do we agree? Now, from 0 over here, you are going up, and pi over 2, you're making a turn in the sine function. Exactly at that point, what is the slope of the sine function? It's flat. If it is flat, then the slope is 0. So does the cosine function describe that behavior at pi over 2? Does it tell you that the sine function is going to be flat at pi over 2 at the exact instant?
Right, now there's not.
It does. Now, even though the sine function is increasing, it is increasing with a magnitude that is decreasing, right? So you're climbing up the hill, right? And you are about to make a turn. So in magnitude, you are decreasing, but you're climbing up towards 0 because you're about to make a turn. That's exactly what the cosine is telling you. In magnitude, it is decreasing and it's approaching 0. See the interpretation?
Yep.
Now, when we do, the derivative of cosine x, it is going to come back to a similar picture, similar interpretation. But are we clear as to why this is true? Yes?
Wait, can you repeat that?
At pi over 2, the sine function is making a turn. What is the slope of the tangent line at pi over 2? When it's making that turn?
Wait, are you talking about sine or cosine?
The sine. Slope of the tangent line at pi over 2.
0.
0, right? So cosine supposedly describes the behavior of sine in terms of the derivative.
I get it now,
Yes? So what I meant by decreasing in magnitude, in the sense as you climb up, you are reducing the slope and you're headed towards the turn. So you're approaching the flat line. Okay.
And that explains why sine x or negative sine x is back there, because as you're going from 1 to 0 again, the magnitude is going.
Very good, yes. Are we clear? Okay, I'm going to erase the visual explanation. Now we can go for the algebraic one. How do we find the derivative? Difference quotient. So we are going to start with the difference quotient.
I'm supposed to say, because I remember at the very least.
So, go ahead.
Oh, no, I was just saying how, I remember how you were saying how there was an extra chapter as well that we didn't go over because it wasn't exactly necessary talking about what exactly the derivative is. That's why. But in any case, though, for the derivative quotient, I believe, isn't it f of x plus h minus f of x over h, with h approaching 0 as well?
We'll get to the limit part in a second.
Oh, okay, my fault.
So we know the difference quotient. The difference quotient is simply f of x plus h minus f of x divided by h. Replace x by x plus h, end up getting sine x plus h minus sine x divided by h. Great. If I took the limits of that, by definition, we are going to end up with the derivative. So take the limits on both sides. Good. Can I directly apply the limit right now?
Sine x plus h.
I hear yes, I hear no. Why not? It'll be exactly 0.
No, the denominator will.
The denominator would be 0. The numerator will also be 0, right? Now, what did I say about 0 over 0 when finding limit?
You got a 9 once.
Right? We can't do that. 0 over 0, not good. So it's an indeterminate form. So we have to do some sort of algebra or algebraic trick to get to a point where we don't have to end up with 0 over 0. Goes back to the problems where we did radicals. Anytime we had a square root function and we got 0/0, what did we do? We multiplied and divided by the conjugate, did some algebra. Eventually, it ended up becoming not 0/0, right? So I've got to do something here, but since these are trigonometric functions, we need a trigonometric identity. Let's see if you remember from Appendix D. So if we go back to the sum formula, we know sine A plus B is sine A cosine B plus cosine A sine B. Yes. What is A in our difference quotient? X. What is B? H. So sine X cosine B is H. Cosine H, sorry, cosine X sine B, which is H. And we end up having minus sine X divided by H. Good. Now, oh, of course, the limit sign here. Long time ago, I mentioned when you take the limit of the difference quotient, something magical happens if you did everything right. What is it? What? Go ahead. H should disappear, but before that step,
The original function.
the original function has to disappear. In this case, that is sine X, it needs to go away. Let's see if it goes away. Going to erase this one. Oh, we can't.
Still a beautiful day.
So when we apply the limit, what happens to cosine 0? As h approaches 0, what happens to that term? It becomes 1. It becomes 1. What is 1 times sine x? Sine x. Sine x minus sine x. It'll get cancelled. So when I apply the limit, that term and that term, it'll go away. Do we agree? Okay. Now, that would simply leave us with cosine x sine h divided by h. Good, because I've applied the limit, the original function disappeared. So I have this. Would this limit affect cosine x? Yes, no, no, because the limit is for h. What we have is cosine x, so I can pull it up. Agree? Yes. Good. Oh, but they so far. Where do we go from here? If I apply h approaches 0, sine 0 is 0, 0/0, indeterminate form, no good. So what should we do? Abort mission? So since I know that this limit is going to be 1, I'm replacing it by 1.
Okay.
And cosine x times 1 is cosine x. Are we clear? So this works. We're not making stuff up. Yes.
What happens to that cosine h, did it become one?
This one, it becomes one.
Why?
So cosine 0 is one.
Oh, yeah, that's what you're.
Look at our graph when we first started. At 0, cosine is 1. Good. So we're not making stuff up, it actually works. Can I erase?
Yep.
Okay. So I'm going to only do sine, cosine, and we're going to try tangent. And once I show that all of them work, we're just going to go to the table of derivatives and write the formulas. Every single one of them will work. You just have to try, and I'll let you know how to verify them. I hope you guys try. The next step is to verify the derivative of cosine x is negative sine x. Good. So where should we start?
Oh, start with a D2.
Thank you. Okay.
So that means f of x plus h.
F of x in this case is cosine x.
And that minus, at the very least, cosine x over h. Then we're going to use an identity, at the very least, to factor out cosine x plus h. And then from there, we're just gonna keep on solving until eventually we see negative sine x come home.
Well, he just put everything summed up in like 10 seconds.
Well,
But I want you guys to try. So which identity should we use now? There is one for cosine a plus b. I'm not going to tell you what that is. I want you to look into your notes.
For memory, isn't it like cosine A, cosine B, and minus sine B?
Very good, Gio. So,
if we're sine is the same, cosine is different.
so cosine a plus b is cosine a. Cosine b, is it plus or minus?
So minus.
Minus sine a, sine b. So use this identity, plug it in there, and tell me if you get negative sine x. You will, or else my life is meaningless.
Those are the best kind of changes.
Very true. So I kept that part away from you guys so that you could figure it out this time, and some did ask that question, which is great. So cosine x plus h is cosine x. Cosine h, cosine a, cosine b, minus sine a, sine b. Yes,
Lovely expression.
minus the original function, cosine x, divided by h. Correct?
Yeah.
May I ask you a question?
Yes.
Why is it you never put that up so you have more space?
So I don't put this up because if I did that, I've got to move the camera and spend time.
Really?
Yeah.
The camera moves because that thing goes up.
I have to use this to move.
Oh my god.
So that's why I use this. So I have to pause and then go back here. You know, pull that up, pull that down, and also, you know.
You want to, it's like Dr. Shane's microphone from last semester.
So this is what many of you did, which naturally I understand why you did it, because I told you so. That step went to this, and the reasoning that I used was, okay, what happens with the original function when you evaluate the difference quotient? It goes away, correct? So h of 0, 1. This would be 1, yes. Cosine x minus cosine x goes away. Yeah, great. Now, some of you asked me this question. They didn't kind of buy it as to why I went from here to there. Even though my reasoning was the original function would go away, which is true of different equations. Can I erase this side? So what I then eventually waited for you guys to recognize is, sure, I can put 0 here and make the argument the original function is will go away, and 0.
Will these problems always approach 0, where it could be 1, 2?
What do you mean by that?
Like, you know how h approaches 0, but you plug in 0 for cosine h, and it gives you 1.
Oh, this should always approach 0.
So it's
the
all-
definition of derivatives.
Okay.
So I could plug in 0, cosine 0 is 1. But if you change your thought process of going from, the original function goes away, you're thinking, well, 0, cosine 0, 1. Cosine x minus cosine x is 0. What about that h? That lonely h is still there. I completely ignore that when I've made that logical argument. Oh, the original function has to go away. That makes
Couldn't you take
sense.
negative sine x out though?
So since the common denominator is h, I can split it off, right? This term minus that term divided by h minus sine sine x times sine h over h. Did you see what I did? Yes.
Why wouldn't you just simply take out the negative sine x itself, instead of just putting the negative out there?
Patience, Alejandro.
I'm just saying.
One step at a time. There's always a reason behind what I do. So when I put 0 here, that's exactly what we did in the previous problem, this problem. That would become 1, and we immediately said the function and the whatever we have, the original functions went away. We did our difference equation right. But there is another condition, another thing that should happen with a difference equation. You guys mentioned it earlier. 1, original function disappears. 2, h has to disappear. That h was still there, sadly, right? And if that is the case, these two will cancel, giving you 0 divided by 0. By all means, that is an indeterminate form. So how did I jump from here to there with that explanation that I gave last time? Some of you asked me that question, which is great because you recognize that something is going on here. This is what's happening, and it is true in the previous problem also. There is a cosine x in common, correct? If I pull that out, I would have cosine h minus 1 divided by h. Yes? And then I have this term. Majority of you who verified went directly from here to here, and some paused and asked me, but why? Which is a good thing. Can you tell me why? Why did this term just disappear? As apart from my reasoning that this and that should cancel. Yes. Yeah.
I'm thinking like when you apply the limit, it just goes away. It just doesn't everything cancels out like you said, so why would you need that? Now you have another thing that you can do.
Well, if h approaches 0, it's 1 minus 1, 0, 0 over 0, that's no good, correct? So something must be true here. Alejandro.
At the very least, one of the important limits that we talked about before was cosine x minus 1/x, which is equal to 0.
At the very beginning of class, I wrote two limits and I said they are important. One was sine limit x approaches 0, sine x over x. The second was limit x approaches 0, cosine x minus 1 divided by x.
However, and as much as I understand that, there is one point that I still do not get, and it kind of goes into his question. Why exactly is it that we separate these into two terms when, again, these were both one conjugation? We didn't have to separate them considering that we could have just done cosine x times that we just did. And I know you explained it, it's just I still don't fully get that.
You mean to say why we go from here to here?
Why exactly do we split them into?
Because I'm trying to give a reason as to why this term and that term disappeared, right? In the previous case, when I verified, I said when h approaches 0, you will have sine x and minus sine x. The original term, original function goes away. That is something you know that happens with a difference quotient. But something else should also happen. The h has to disappear so that when we apply the limit, we don't have 0 over 0. That part I didn't mention last time because I wanted you guys to think. And some of you did think and asked me, well, you went from here to here, but why did this happen? And that's exactly what I'm doing here.
I was just thinking that PEMDAS would explain it well, parentheses for the very least, exponents, multiplication, division, addition, subtraction. So right here, at the very least, since that's multiplication, that comes before any sort of addition or subtraction, boom, then you get cosine x times cosine h. H is 0, so boom, you then just get cosine x times 1. You get cosine x minus sine x times sine h.
Okay. Yeah.
I was gonna say, why, you're looking at it weird because, look, even if you took a look, cosine minus cosine x is what? It cancels out, so cosine h over h is just 1.
No. Cosine h over h, if you did that, you would get 1 divided by 0, right? You get divided by 0.
But I thought it was like an identity. Or
No, that only works for time. No,
Well, that's what I was, because that becomes, the left limit becomes 0 based on what you wrote down, and then you just take sine out, and put it in front,
Exactly.
and that's why that becomes 1.
so when I apply the limit, that's gonna go away. So you would have cosine x multiplied by 0, and that is why this goes away. That's the rationale behind it. If you go back and look at our previous problem, this is what we had, yes. And I said, when h approaches 0, sine x, original function, will go away. But we didn't say anything about the denominator h, yes. So we completely ignored and glossed over. The reasoning behind it is, sure, those two get cancelled, but the denominator h sort of disappears, just like it always does with our regular difference quotients, because of this limit. If you pull that sine x out, I'm going to erase this part. I would still have that in the previous problem. Do you agree? And what is the limit of that? 0. So all I'm trying to do in this problem is to explain why cosine x and the original function goes away. Explain here as to why sine x cosine h, and the original function goes away. It goes away because of that limit, the second important limit that I wrote at the beginning of class. Good. So I have justified that this is going to go to 0. So that's the only part that is left, and that equals that. Yes. Now that everything is okay, limit of h, will it affect sine x? Would it affect the -1? No. So I can pull that out. And what is that? So the derivative of cosine x is negative sine x.